So my name is Marcel. I've been working on TEEzz, fuzzing trusted applications on commercial off-the-shelf Android devices with all of the beautiful people you can see on this slide. And as you all know, smartphones have become an integral part of our lives. They support many, many use cases. Some of them are more critical than others. And the data that is processed here is partially critical, meaning it is exposed to the threats that we have on these devices, like a malicious app being installed or the device simply being stolen. And the last level of defense that we have, especially on Android mobile devices, is the trusted execution environment that takes care of your biometric identifiers, PIN, pattern, password, or cryptographic key material in general. And what you will see on ARM-based devices that ARM TrustZone is the hardware foundation for the trusted execution environment. So now let's take a bit more brief detailed look into ARM TrustZone. We will find that we have 4 privilege levels, these exception levels that you see on the left here. And ARM did this world split where you have a normal world execution context, also referred to as the rich execution context, where you find the stuff that you're familiar with. On Android would be the Linux kernel and the Android userland stack. And then you'll have another execution context called the secure world or the trusted execution environment, where a bunch of proprietary blobs by the vendor are usually executed. And these security critical services are usually encapsulated, modularized in so-called trusted applications that you see in the upper right here. And client applications can make use of these services using some sort of inter-process communication mechanism. But they cannot do this directly. They actually have to turn to higher privilege levels, because only at the bottom here, the secure monitor is able to switch in between these execution modes. So then this work, TEEzz is a black box fuzzer for trusted applications which suffer from bugs, especially memory corruption bugs, as like prior work and our work here shows. So now let's look into why is it challenging to fuzz trusted applications in general. So first of all, we have, if we fuzz on a device, very limited introspection capabilities. So in a world where we have gray box fuzzers with like very capable introspection capabilities, we have usually coverage-guided feedback or some other sort of feedback mechanisms. Due to the isolation enforced by ARM TrustZone, we don't have this when we fuzz trusted applications on a device. Then secondly, data is usually shared in like huge chunks of memory blocks in shared memory, and this data in there is pretty complex. So just arbitrarily mutating the input for fuzzing will lead to exploring an input space that is way too large. And thirdly, these trusted applications are stateful, and if we don't really account for the state transitions in trusted applications, we will not reach meaningful code. So in TEEzz, which is a black box fuzzer, the design of TEEzz was led by the following observations or intuitions. And the first one is the TE does not exist for its own purpose, right? Usually in the Android context, we usually have some sort of system service, and a subcomponent of the system service encapsulates this client application that I've been talking about before. And there's usually some like high-level API that has like a very like semantic-rich API where we have like meaningful types, and getting to lower levels of abstraction, these types just vanish, and we just move data back and forth between the TE and the normal world execution context. And on the other hand, if we come from a fuzzing perspective, we'll see that fuzzing from this higher level device will not really lead to interactions passing through to the TE, because there's a lot of sanitization logic in these libraries. So we would prefer to fuzz at a lower level interface where we have a lot of control over our input. And the intuition of TEEzz is the following. We kind of want to capture the seeds at a high level interface, record seeds in a type-aware way, and be able to propagate these types to everything we see at a lower level interface to make use of the powerful control that we have here. So let me briefly walk you through the different phases of TEEzz. We have 4 of them. The first one is client application identification. So there's no enumeration mechanism usually that just tells you which of the components in the Android context is actually talking to the TE. So we built a little bit of automation to do that. Once these are identified, we can extract the interface descriptions of these client applications, and we do the following thing. So we turn these interface description in an AST. Then we generate type-aware mutators for these interface definitions. I will go into this in a bit more detail later. And then the second thing that we do, we create something that is called a dynamic binary instrumentation introspection recorder, which is a fancy term to say we have a hook into a function which allows us to scrape memory in a type-aware way that we can later leverage as a type-aware seed. Okay? And with these like fancy mutators and this fancy seed corpus, we can then fuzz trusted applications on the device. So now let's look into a little bit more detail of these introspection recorders and these mutators that we generate from the abstract syntax tree of these client application interfaces. So here's just a simple example for an interface definition. You see a function that takes a pointer to a struct. This is C. This struct definition is also here. It has 3 members, one of them being an enum that has 3 values, right? So we generate the AST from this, and then the 2 outputs that I've been talking about is these introspection recorders, where we generate logic that can dynamically hook into these APIs, and when an interaction happens, we can scrape each of these parameters according to its type, since we know the layout, and persist it and make it part of our seed corpus. And the second thing here is these type-aware mutators, just a simple example. We have seen this enum here, and if during our mutation strategy we would see this enum in the context of the struct coming up again, we know that the input space of this enum is likely to be in the range of these 3 values that are defined, and not the 32-bit value space that the underlying int would actually occupy. So it would reduce the input space significantly to mutate it in this way. So let's look a little bit more deep into these introspection recorders. Here an example of a function that takes 2 parameters, one of them pin, and another one being kout, which is an output parameter. First, pin is a nested struct, and kout is a simple flat struct. And I'll just show you a brief example of how pin looks here. There's a pointer to an array of the length of 3, and here we see the 3 different entries in this array. And what we do at a higher level with these introspection recorders is hook into the interface and scrape these parameters from memory in a type-aware way, so that we can store them at this level of abstraction. We do this for input and for output parameters. And then at a lower level, we do the same thing, just at the level where we don't have any sort of type information and where we only see raw bytes, right? And then we do something interesting. We correlate this type of information down to the raw information we see to obtain type-aware seeds. And we do this for input and for output parameters again. So now you might ask, why do we do this for output parameters? Well, we didn't address this state awareness issue yet, right? And what we see in trusted applications is that we can account for these finite state machines by just taking care of the value dependencies in a sequence of calls. So taking care and recording the output parameters as well, we have a chance to see that an output parameter is later in the sequence used as an input parameter, and thus implicitly taking care of the state machine of our target. So a couple of highlights of our evaluation. First, the bugs that we found. So we fuzzed on 4 different devices, covering 2 different proprietary trusted execution environment. We found 40 unique bugs and got 1 CVE by Qualcomm assigned. We also fuzzed Opti, which is an open source reference implementation for TrustZone-based TEEzz. And here, targeting the trusted application available for Opti, we found 13 previously unknown bugs. So another highlight of the evaluation is this ground truth experiment here, where we wanted to know, so we have in TEEzz a fancy mechanism to capture seeds, right? But what does this tell us actually about the coverage we achieve in the target? So we took Opti and we modified it in a way so that we can actually measure coverage. And we built we integrated AFL into this too, so that we have something we can evaluate against. So and TEEzz, having all of its fancy seeds, can actually achieve a higher coverage than a gray box fuzzer that actually makes use of coverage in certain scenarios. So here we could show that we can outperform gray box fuzzers with a very nice and state-aware seed corpus. So that is all. Let me wrap up. TEEzz is a state and type-aware black box fuzzer that we use to fuzz trusted applications. I hope I could draw some attention to this problem of memory corruptions and bugs in TEEzz in general. Introduce you to our fuzzer and our findings, and more details you can get from the paper. I'm looking forward to your questions. Thank you.
Thank you very much, Marcel. If you have a question, please come up to the microphone. So what is the total amount of manpower do you need to adapt to yet a new TE?
The amount of manpower that you need to adapt to another TE. So first of all the TEs that we see out there are very heterogeneous, right? And completely depends on the vendor.
Okay. No. Yeah. So I want to use your approach, but I have a new platform that I want to do it on.
Yeah. So there are only like a handful of platforms out there, right? We covered 2 here. Another very important one would be the one by Samsung. And Samsung, in a sense, is very similar to Huawei, since they're building on top of the global platform API standards. And I don't think that would be much work to do, like a week or 2 for like a specialized engineer.
Okay. That's reasonable. Can you go to the microphone? Oh,
maybe I missed during the presentation, but the hooks, are they generalized for a certain type of function, or do you have to have a hook per function?
You have a hook per function. So like in the back, we use Frida. Like there's a very mature dynamic binary instrumentation toolkit. And we can hook into functions on a function basis. So these functions are...
It can be like a function type, like if a function have 2 input and 1 output, versus a function would have 3 input and 2 output, and can create the hook for those different type of functions.
Yes. So I think what you're aiming at is, are these function hooks that we're generating generalizable, right? And so what we do is actually we take the function definition, and automatically from these function definitions, according to the types consumed by the function, automatically generate the introspection logic. So the answer to your question is yes. I believe in most of the cases it should be generalizable.
Okay, thank you very much again to the speaker.